Hello everyone, welcome to today's video. We'll hop right into it. We're going to be talking about exponential functions and their graphs. So we'll start off with the definition and look at the formula. We'll talk about exponential growth versus decay. We'll talk about finding the equation of an exponential function if we know a couple of points on the graph. We'll look at continuous growth, and that involves the growth constant e. And we'll look at the shape of graphs and transformations of those graphs. So there is great news. I became insanely wealthy overnight, and I figured what better way to celebrate than to share it with all of my students. So I'm just offering you two different ways to collect your payment here. One is you can just take $1 million cash right now. I'll just give it to you, no questions asked. Walk out the door with it. Or I will open up a bank account in your name, and I will deposit a penny, and then I will double the balance every day for a month. And you can decide right now which one sounds like a better deal. I think the idea here is that $1 million sounds pretty good. A penny doesn't seem like that much. A month isn't that long. But why else might I be asking this question other than it's a math class and we're talking about exponentials? So let's just investigate here. We'll take a look at kind of what happens over time. So today's day one. I'm giving you that penny, and if you open that account, I'll put it in there. And then tomorrow it'll double. So tomorrow you'll have 2 pennies. There'll be 2 cents in there. Okay, and then it'll double again on day 3. There'll be 4 cents, and then it'll double again, and now there's 8 cents, and it'll double again, and now we're up to 16 cents. So we're getting close to a weekend, and there's not that much money in there. So maybe it's looking like the $1 million was maybe a better choice. By the time we get to day 9, there should be $2.56, which is better than 16 cents, but it's still a long ways off from $1 million. So we'll head into the future a few more days. On day 13, there will be $40.96. So we're getting close to halfway through, and we are a long ways off from $1 million. By day 21, things have been doubling for a while. We're actually up to 10,485 and 76 cents. So, not too bad. But still, what's that? Just a little over 1% on our way to $1 million. Is that right? 10,000, 100,000 would be 10%. Yeah. So we still have a long way to go, and there's only a week left. But by day 28, we are going to be at 1.342 million and 28 cents. So it's already looking pretty good by day 28, and there's still a few more days to go. By day 30, there will be 10,737,418 and 24 cents. So yes, it does look like taking this magic penny that doubles every day is going to be the right choice here. The sad news is that I'm not insanely wealthy. This was just a motivating idea for a math video. It's a common one, so I didn't come up with this, but this models just how fast things can grow when we're looking at exponential functions. So what we've got kind of built into the background here is this kind of doubling function. The indexes are a little bit off, but that just means that the graph is being shifted around a little bit. But I just wanted to take a look at kind of where the variable lives in all of these different situations. Tells us that the outputs are growing faster and faster. So what I'm saying here is kind of looking at this other graph. If we're looking at input values of 1, 2, 3, 4, and 5, well, 2 times x, 2 times 1 is just going to give us 2. It's going to give us 2. 1 squared is actually just 1. And 2 to the 1 is just 2. So as we look down at 2 now, 2 times x is going to give us 4. 2 squared also gives us 4. And 2 to the 2 also gives us 4. So it looks like things are staying kind of in the same spot here, but now I think we should see some better growth. 2 times 3 is 6. 3 squared is 9. And 2 to the 3rd power is 8. So it looks like the squares are winning, but I think that we will see a change here. For 2 times 4, we get 8. 4 squared gives us 16, and 2 to the 4th is also 16. So it looks like the exponentials are catching up. Once we get to 5, 2 to the 5 is 10. 5 squared is 25. and 2 to the 5th is 32. So at that point, the exponentials are starting to grow faster. So you can see that they kind of start in the same spot. Things are looking relatively the same, but then they start to grow a lot quicker and will continue to grow even more quickly after that. So let's look at the definition for exponential functions here. For any real number x, an exponential function is a function of the form f of x equals some constant a times some constant b being raised to this variable x here. And we need these two conditions. We need b to be positive. If the base of this exponential is not positive, then we don't get something that is defined at a lot of points. We don't get a very interesting object, or maybe it's very interesting depending on how you look at it. And we also need b to not be equal to 1. If the base was equal to 1, then we would just get this constant function, and that's also not very interesting. Here, a is a non-zero real number. If it was 0, we again wouldn't get an exponential function. We would just get the 0 function. And it's called the initial value. So we'll look in a second of why we might call it the initial value. But the domain here is all real numbers. We're allowed to plug any number in. We'll get some value out the other side. The range, if the initial value a is positive, then the range will be all positive numbers. If the initial value is negative, then the range will be all negative real numbers. And zero doesn't happen for either of them. And then the y-intercept is the point 0a. The point 0, 1 happens on a lot of the parent graphs, and then we'll get stretched up once we multiply by that initial value. And there is a horizontal asymptote at the line, y equals 0. So there's just a bunch of different examples down here. We've got f of x equals 2 times 3 to the x. You can see that the y-intercept here is at the point that is 2, 0. Yeah, the numbers are not easy to see, but this is the point, 0, 2. Because this is where the initial value is at 2. This is where it starts, where the graph starts kind of, if we're thinking about time, time usually starts at 0, so that is where the initial value would be. Looking at this one here, 1/2 times 2 to the x, we still have this kind of same shape that's growing, but now the y-intercept is down here at 0, 1/2, because that is what the initial value is. The third one here, we've got things flipped over because we have a negative leading coefficient. So hopefully that's not surprising that, what the graph normally might look like for just e to the x got flipped over the x-axis there and also stretched a little bit. And you can see that the y-intercept is down here at 0, -2. So just some different shapes that these graphs can take. All right, now we'll talk about exponential growth versus decay. So if we're analyzing some function, f of t equals a times b raised to the t. So still same idea, we're just changing the variable from x to t because we're usually talking about time when we're modeling things with exponential functions. And here f will model exponential growth or decay, and we always see the following. So f of t gives us the total amount at any time t. So if you want to know what's happening after 3 seconds, if time is in seconds, then you plug in 3, f of 3, and you can find out exactly what amount happens at that time. The constant a, as we said before, is the initial value because it is the total amount when no time has passed. So when t is equal to 0, well, that tells us we would just plug 0 into the function. Once we plug that in to a times b to the t, we get a times b to the 0. B to the 0 is always just equal to 1. So this is just b to the 0. It's always equal to 1. And a times 1 is just a. So what we see here is just by simply plugging in 0, which is the initial time, we always just get a out the other side. So that is why we call a the initial value. And then we have the constant b. This is the base of our function, the exponential function. And this will tell us whether we have growth or decay. We can also find the rate of growth and decay from the b value as well. So if b is positive, they're all positive, but if b is bigger than 1, then the function models growth. So having that kind of zooming off to infinity effect. And then we can use this little relationship, b equals 1 plus r, where r is the rate of growth. So we'll look at an example here in just a second where we can find those things. And then, like I just mentioned, b is always positive, but here, if it is between 0 and 1, so it's some sort of fraction, 1/3, 1/2, 5/6, 1 over 112, any sort of positive fraction, then we get this decay. So it'll be kind of decaying and getting closer and closer to 0 as it goes down, otherwise, unless it shifted around. And then we can also find the rate of change by using this relationship where the base is going to be 1 minus r, where r is the rate of change. So looking at a couple examples here, we want to determine if we have growth or decay, and we want to find the rate. So for the first one here, we have some initial value, 150, our base, our b, so this is our a, and this is our b. And the b is where we want to focus to see if we have growth or decay. So since 1.049 is larger than 1, this means that we have exponential growth. I also know that b, which is 1.049, is equal to 1 plus r. So if I want to know what r is, well, I can just subtract 1 from both sides. And this tells me that r is equal to 0.049, which is the same as 4.9%. So depending on how things are being asked, you might be asked to give it as decimal, but often we represent it as a percent. So 4.9% is the rate of growth in this example here. So the rate of growth is 4.9%. For the second one here, we've got some initial value of 72. And here, I forgot my t on this one, so there should be a t up there. The base is 0.89. So here we've got 0.89 being less than 1. So this tells us that we've got exponential decay, which means the graph will look something more like this, getting closer to 0. And then if I want to find the rate, well, I know that 0.89 is equal to 1 minus r, and I could do a little bit of algebra there, and I could see that r is equal to 0.11. So this would be the same as 11%. So that is how we could find the rate of decay. So that's it's still the rate, but is the rate of decay, and it's at 11%. Rate of decay. So we're always kind of looking at 1 because that would mean things would be 100% of where they started from. But is it going to be growing? Well, that's more than 100%. Is it going to be decaying? Then that's going to be less than 100%. But we'll always be positive there. All right, next we'll look at an example here of finding the equation of an exponential function that's passing through a couple of points here. So I always like being able to just look at a quick sketch so I can get an idea of what's going on here. And then we'll look at seeing if we can't find the equation. But I know I've got something going on at 0, 1/2. So, well, I'm going to need to get up to 8. So I can at least put in 1, 2, 3, 4, 5, 6, 7, 8. Make it a little taller. So there's 8. I know I've got a point at 0, 1/2. So there's a point at 0, 1/2. And I know I've got a point at 2, 8. So this must look something like that. More or less. Okay, this is this point 2, 8, and this is the point 0, 1/2. Okay, so we got something that looks like this. I want to find the equation. Well, I know that all equations will look like f of x equals a times b to the x. And I just need to go figure out what a has to be and what b has to be. So let me just go use some points here that I know and start plugging them in and seeing what's what. The fact that one of these points is 0 is actually insanely helpful because that tells me I can plug in 0 to my function here. It tells me that since the point 0, 1/2 is on the graph, that this should be equal to 1/2. F of 0 is equal to 1/2. That is literally what this point tells me. But I also know that I'm plugging 0 into this function. So I have a times b to the 0. Now just focusing on this portion here should tell us a lot of information. This tells us that a, remember that b to the 0 is just 1. So this says a times 1 is equal to 1/2. So a must be 1/2. We also could have just gotten that because we know that that's the initial value. The initial value is the y-intercept. So we could have gotten that for free, but by plugging it in, we can actually get some information and just get it directly that way as well. So now we'll use the other point to see if we can't figure out what we figured out A, so now we need to figure out what B is. So let's just use the other point. Knowing that A is 1/2, I know that f of 2, I know it's going to be equal to 8 once we're done. That is what this point is telling me, is that if you plug in 2, you get 8. But I also know that A is 1/2, and I've got B to the 2, or B squared there. So now I can use this portion to solve for B. So if I multiply both sides by 2, then I get just B squared. Those would cancel. Just B squared is equal to 16. I could take the square root of both sides. That will give me B is equal to plus or minus 4. There are two numbers that once you square them give us 16, but the base always needs to be positive here. So we can go and get rid of that. We know that we can get rid of the negative solution, and so B is just 4 here. So kind of putting it all together, now we know what B is, we know what A is. So if I want to write down the equation of this exponential function, we can call it f of x is equal to 1/2 times 4 to the x. And there we go. There is our exponential function. All right, next we're going to talk about continuous growth. So this is a special type of exponential function, and it will be increasingly important to you as you get into calculus. You will see this, a version of this e to the x function a lot, and you will be glad to see it. But for right now, for all real numbers t and all positive numbers a and r, continuous growth or decay is represented by this formula here. So the base of this function is this number e. And as a reminder, e is about 2.71828 blah, 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 blah. It is a transcendental irrational number, just like pi is. It has this non-repeating decimal expansion. It's a hard thing to define. You can define it using limits in calculus. There's different ways to define it. For now, we're just going to reference it and remember that is an important thing here. But for here, r is still going to be the rate of change, whether that is growth or decay, and t is still going to be the time elapsed, and like I said, e is the growth constant here. Again, if the rate is bigger than 0, we're going to have growth. If the rate is less than 0, we're going to have decay. Here we have a person investing $1,000 in an account that's earning a yearly rate of 10%, compounded continuously. How much was in the account at the end of 1 year? So since this has this number e in it, we're going to need a calculator to compute what's going on. So having a scientific calculator will be helpful. I've got one here at the ready. I have not done this problem yet. I like to do them often in the moment so I can think along with you. But a person invested $1,000. That's going to be our initial amount here. So if I'm going to think about just coming up with a formula, A of t is going to be $1,000 as the original investment. That's the initial amount at time 0, earning a yearly rate of 10%. So I'm going to do e to the 0.1, that is my rate, times t, and that is going to be my time. And what I want to know is how much is in the account at the end of 1 year. So we want to look at is A of 1, which is going to be 1,000 times e to the 0.1 times 1. So 1,000 times e to the 0.1. And I don't know that off the top of my head better than anybody else, so we'll put it into a calculator. We've got e to the 0.1 gives me that, times 1,000. And I get $1,105.17. What is nice about money problems is you never need to be told how many decimal spots to round to, because you always go to the nearest cent. So there we go. After a year of having this person's money continuously compounded, so that doesn't mean that it's compounded every year, but even faster than every month, every week, every day, every minute, every second, every millisecond. This is compounding as quick as you could imagine. So this is just about the best rate that you could get in terms of compounding. But there we go. We got the answer there. So hopefully that is a good refresher of continuous growth. All right, lastly here, I believe this is last, yeah. We're going to look at sketching the graph. of this given function here. First, we'll sketch the parent graph, and then we'll look at transforming that through the different transformations that we see here. So I would say that the parent graph here, we could call it, I don't know, call it anything else, h of x or something, is going to look like just 1/3 to the x. So this is our parent graph here. So if I'm just gonna kind of sketch this on roughly like that, that's not how this looked. That would be what it looked like if the base was bigger than 1. Since the base is between 0 and 1, it's going to look like, well, let me draw that a little better. It's going to look more like this. And this is going to be the point 0, 1, because that is going to be a point on every parent graph, 0, 1, unless it's flipped over the other way, but that'll be the negative we deal with next. And then I know at 1, this should be the point 1, 1/3. So just thinking about plugging in those values here, if I plug in 0, I always get 1. If I plug in 1, I always get 1/3. And these will be kind of the values that will move around as I'm thinking about altering this graph. So next, let's look at moving this around. We'll put the negative in front. So I don't know, negative h, I don't want to go through all of this, but we'll say that now applying the negative, this will be the green one, negative 1/3 to the x means that everything's going to get flipped to the other side of the x-axis here. So we're going to get a reflection. So we're going to have a point here, and this should look now something like that. And this is going to be, I kind of missed, but this is the point 0, negative 1, and this is going to be the point 1, negative 1/3. So there is the negative being applied. That gives us the reflection over the x-axis. Now what we'll do is we will shift everything to the left by 1 unit. So we'll do this one in blue. Now I've got negative 1/3 x, and adding 1 to the input means that we're going to shift things left and right, or any adjustment on the input means we're shifting left and right. Since we are adding 1, that means things are getting shifted to the left by 1 unit. So that means that this point is going to get shifted over 1 unit, and this will be now at negative 1, negative 1. And this guy is also going to get shifted over 1 unit, and this is going to be the point 0, negative 1/3. Kind of, I can write that in a better spot. Let me draw the graph. Something like that. Oh, I don't want it to actually cross because it's still just getting asymptotically close to 0 there. And then this is the point 0, negative 1/3. All right, so there we go. The blue graph here is our final result. We've got a few other subgraphs in there as we go. What else are we asked to do here? We're asked to state the domain. So the domain of this function is all real numbers. We're allowed to plug in anything that we want, and we will get a result. We can also take a look at the range here. And just by looking, everything lives below the x-axis. So that means that anything from negative infinity up to 0 will all be part of the range, but not including 0. Remember, that is an asymptote. It will never actually hit 0. So I'm using the open parenthesis notation there. There's our domain, any range, and then the asymptote. We have a horizontal asymptote. At the line y equals 0. And there are no vertical asymptotes. So I know that these things are shooting off, and they look like they're getting asymptotically close, but they're not. They're just growing without bound in either or in the negative direction. So yeah, there we go. There is a quick sketch with all of the details there. And I believe that brings us to the end here. So good luck with the homework. Please let me know if you have any questions. I'm always happy to help, and I will see you in our next video.